Yeah, exactly. This is recorded, but people sometimes say serious things. So it's my pleasure to introduce Miles Stoudenmire. He is my colleague at the Flatiron Institute, where he basically runs the Tensor Network group at the CCQ, so the Center for Computational Quantum Mechanics. Miles got his PhD from UCSD with Leon Balance, where he was working on sort of frustrated magnetism, and I guess part of his PhD was already about some new algorithm to use tensor networks to do it. After that, he moved to Steve White's group, which I hope some of you know. If you don't know, Steve White, he's basically the inventor of DMRG, density matrix renormalization group, which is what Miles probably will talk about in some capacity. So I did his PhD there. Then after a short stop at Perimeter Institute, he moved to the Flatiron Institute, where, as I already said, he's currently leading our efforts in tensor network research. And he's basically the main developer, together with Matt, of the iTensor library. So I think there's a bunch of people actually here that probably use this software. It's an open source kind of software to do tensor network contractions to simulate quantum systems. And I think Miles will basically tell us what all that stuff can do. So Miles, the floor is yours.
Great, thanks a lot, Dries, and hopefully everybody on Zoom can hear through this evening. Thanks, it's a real pleasure to be invited. Thanks a lot to Dries, Javad, and everyone else for hosting me and inviting me over to Neighbor Institution to speak. It's a real pleasure. So thanks so much. I'll say a bit about what we do at Flatiron Institute in a minute. So my title is Quantum Computing on Classical Machines with Tensor Networks, and I hope I'll give you an idea of how all three of those concepts connect. And kind of by request, we've been doing lots of different things with tensor networks and sort of relating them to quantum computing. I'll mention one in passing about the quantum Fourier transform, but I'll sort of spend the latter half of the talk speaking about this result we got where we tried to simulate and largely succeeded a particular experiment on an actual quantum device from an IBM group, and sort of how that went and why there's this interesting kind of back and forth going on right now between both of these areas, kind of trying to discover together what are like the hard problems that everybody should be focusing on with respective methods. So let me great, so perfect. So by way of motivation, I don't have to tell many of you that there's lots of excitement right now in the air about prospects for quantum computing, even in the near term, right? So even before we have error correction. You often see headlines about things like that maybe quantum computers will make a big impact on cryptography, but also on you see things about drug discovery, there's some deep disease control. I just clipped headlines that I saw, finance, transportation, chemicals, many different industries. So you have all these different streams of information coming at you, and it sounds like, which one of these is really serious, which one of these is just sort of, how far out are all of these different prospects? So it's important to try to sort that all out. So it's not right now completely clear. We don't have the whole picture. We have parts, precious pieces of this picture. We don't have the whole picture of all the problems quantum computers can practically solve better than classical computers. We have lots of pointers in different directions, and we have a few gems like Shor's algorithm for certain specialized tasks. So there's these different candidates, right? Like the older ones that are in some sense in the best shape, and theoretically still are things that have to do with discrete math, factoring, Shor's algorithm, specific classes of inverse problems, Grover's algorithm. Those have questions about, how soon could we realize them? How robust will they be to do decoherence and things? So you need error correction most likely. You need thousands of qubits. How many thousands of qubits might you need? Or will error correction and overheads come down? Other very different areas, chemistry, but can it scale? How accurate will it end up being? Because modern quantum chemistry methods are very accurate. So can it get below chemical accuracy of large molecules? And then physics simulation, simulating quantum systems, which is what I'll talk about a little bit later. Yes, that certainly makes a lot of sense for quantum computers. It's maybe the best area to think about in terms of likely to happen in the near term. But then, to what circuit depths do you need to go, and at what accuracies, and can you resolve very small energy scales that could happen in like gapless systems or near phase transitions? All these questions about physics come pouring out. But these amazing devices are being built, right? Some right here at NYU. So we should be researching what's the best use to put them for, right? right? And so one activity that helps with this is simulating them. So simulating quantum computers, one reason to do that is it helps us to define these boundaries, like what's really easy, what's really hard. And then among the simulators, tensor networks are, maybe I should have said one of the most, but let's just say, in many cases, the most powerful technique to simulate some of the same systems that quantum computers can also take as input. And then what's been really surprising to me and other people is that in a few cases, although these cases are quite rich areas, like whole things involving transformations of functions and all these other areas, in some cases we started out thinking tensor networks would be simulators, right? So the idea I had was like, I use this analogy of like quantum computing might be this huge cruise ship or something that's leaving a harbor, and the tensor network might be like a tugboat or a pilot boat that's kind of guiding it out of the harbor. But then when you get to the deep water, the tugboat has to turn around, and then the big boat can go out into the deep water. So that was the picture I always had, right? But then it turns out sometimes it's like the tugboat can just keep going and keep going out into the deep water. So we've had cases where the tensor networks in some, not all problems, but certain classes of problems ended up being so powerful we kind of flipped the script around, and we could find out, us and others have found out that some algorithms that we thought were quantum algorithms are actually classical algorithms all along in disguise. You just had to use a tensor network to get to harness them. So then in that picture, a tensor network becomes like a kind of operating system layer in the classical computer that kind of emulates a quantum computer, and you can run quantum algorithms on top of that layer. And then the weird thing is, unlike an emulator, it doesn't slow it down, it actually speeds it up. So it becomes a faster way to run a classical computer, which is really shocking to me for a few different reasons. So that was just the kind of quick motivation. So that was kind of motivation in quantum computing that I just showed you. So let me tell you now more about tensor networks, what they are, how they relate to quantum systems, and then we'll assess kind of a recent claim of quantum utility through this lens and kind of ask, was utility really achieved, and how did we kind of understand whether that line had been crossed or not. Okay, so now in terms of classical methods for quantum systems, now I'm going to broaden out a little bit for a minute, include some other things that go back to tensor networks. The question is like, how quantum can we make classical computers? Like, how much of quantum mechanics can we harness in the classical computing world? So stepping way back, how hard is quantum mechanics? So from the most zoomed out view, or the most kind of worst case view of things, if you have a system of n quantum spins or n quantum qubits, and here I'm just arranging them in a straight line just to be easy to present. They could be, but this could be 2D, 3D, but I'm just lining them up. Then they're described by, one way to describe them is by a quantum wave function. Here I'm drawing it as a big tensor for those of you who know this notation, but for now you could just think of it as a drawing. And inside of this wave function, there's 2 to the n parameters. So if we have n qubits, each qubit 2 states and 2 to the n numbers. This is well known to those of you who do many-body or many-qubit physics. So, and we know, everybody would know that 2 to the n parameters for large enough n, once n is bigger than say 40 or 50, it's really hard to work with something that size on a regular computer, even these days. So, and then exponentially hard in terms of memory, compute that you need. So that's, from that point of view, quantum mechanics is one of the hardest things we know for a classical computer to do, from that sort of brute force direction. So this is also when you run quantum simulator libraries and you use what's called a full state simulator, it just works directly in this representation. So you can only take n to be maybe 20 or 30. So if that's the case, what are we even doing at Flatiron Institute up the street, right? Like, what do we do at CCQ? Do we just take 2 to the n in the teeth, right? And of course, we don't do that, right? So what do we actually do up there? So what we try to do is we try to break through that exponential wall, and not break through it by just hitting it with a sledgehammer, or just throwing more compute at it, but we try to break through it by finding out that wall was more maybe like a pole, and we were just running into this pole, and then if you just go around it, you don't have to run right into it, So sometimes if you just, go in a different direction, it's not exponential actually. And there's many ways to come at the problem from all kinds of directions. Quantum Monte Carlo, high order perturbation theory. This is actually a very rich topic. In fact, perturbation theory sounds like an old topic, but there's a lot of things there. Embedding methods, tensor networks, neural quantum states using neural networks, and then things that have been really powerful and still are, density functional theory, methods like that we use also to handle real materials. So let me just briefly touch on 2 of these besides tensor networks. So one of them, quantum Monte Carlo, you break this exponential by saying that sampling works sort of equally well in all dimensions, unless, there's a little catch, unless the thing you're sampling from has negative probabilities, that brings the exponential back. But as long as you can arrange for the probabilities, the amplitudes to be positive in some basis, you can break the exponential just by sampling over only the important numbers inside the wave function and then just skipping over all the other ones that are very small. Another method that we do is embedding. Embedding, the idea is that you say, what if we could take a small piece of the system and treat it fully with all this interactions and everything? And that's easy to do because it's small. So we can solve something that's small fully, just direct solve. And then we trick it into thinking that it's actually part of a big system by like holding up a mirror to it. So you solve the small system, you see what it does in time. And then you take an easy to solve outside part that's maybe made of free fermions or something that you can just solve very easily. And you wire up the free fermions to hold up a mirror to the small system and trick it into thinking, like, you go in a room and the walls are mirrored, and for a second you think it's a big room, and then it's actually just mirrors. You kind of do that to the small system. You trick it into thinking that it's next to itself, and that actually works really well. And then you make the small system a little bit bigger, and pretty soon you converge to the infinite limit really fast. So it's like a nice way to do it. So there's all kinds of clever ways you can access huge exponential systems like that. And last but not least, I'll spend the rest of the talk using this technique called tensor networks. So let me now reflect a little bit on what they are and like how does it connect up to quantum computing. And my main point of the first half is that the connection is like really, really close to quantum computing in ways that we're only starting to wake up to even in the last year. So main things to know about these methods, tensor networks, and this is what I mainly research and work on, is that you work directly with the wave function most of the time. There's other uses of them now that are developing. I just chatted with a lot of the students about some other uses, but traditionally you just work directly with the quantum wave function, the whole thing. But the way you do that is you use compression to store it. So you store the entire thing, but you store it in like a latent representation. So it's like how you could store, it's kind of like how you could say, how do you store the number one, a list of the number one over and over again a trillion times? You just write 1, a trillion times, and then that's like a very short way of writing that list of a trillion numbers, right? Sort of like that, like using a zip file to store a large file on a computer, right? Just compression. But then what's really interesting about this is that when you do this, you kind of closely mimic a quantum computer in many specific ways. So it's like you compress the wave function into a box, and then if you opened up the box fully, out would come exponentially many numbers, and your computer would catch on fire and you'd be done. But what you do is you open the box a little bit, and you just like peek at part of the system, and then you operate on that part, and then you close that part of the box. And you open the box from a different side, and you do something to it, and you close it back. And by just acting on like little parts of the wave function, you can actually do lots of things, like you can act with gates and so on. So let's see how each of these points works briefly. So why does a tensor even come up at all? What do I mean by tensor and all of that? So let's say you just have a general wave function of n qubits. That's what it looks like. That's just the most general thing you can write. And I would argue that whether or not you like tensors, there's a tensor whether you want it to be or not. So the idea is that you say there's a basis of these qubit variables, S1 through Sn for n qubits. And each of these could be 0 or 1, so there's 2 to the n different basis kets that you have. So all the real information is in the amplitudes. It tells you how much weight to put on each of these kets and whether that weight is positive or negative and so on. And just by inspection, that forms a big tensor. There's the amplitudes within indices that match for the qubits. That's a big tensor whether you want to think of it that way or not. So there's always a big tensor at the heart of a quantum wave function. And then in the past, that was considered a pretty useless observation because you'd say, well, it's a big tensor, but it's too big. You can't do anything with it. So let's come back to that point. But what do I mean by tensor, first of all? So all I mean by tensor, I don't mean anything too complicated. I'm not talking about how do things transform under different group symmetries. I'm just talking about multidimensional arrays when I say a tensor. So all I mean is a vector is a tensor with one index that, so you can talk about its components. You can say v2 equals 3 because the second entry here is 3. A matrix is a tensor with 2 indices. The 1, 2 entry of this matrix is 7. An order 3 tensor is just an array of numbers with 3 indices. So you can say the 1, 1, 2 entry of this cube of numbers is the number 5. But this already hints that this notation is not going to scale up very well. Beyond 3 indices, it's going to be hard to draw. How do I draw a 4-dimensional cube? Numbers is going to be very bad. But that's all I mean by tensor, just a multidimensional array. So to actually deal with dimensions beyond 3, we use this thing called Penrose diagram notation. And it looks like a drawing, but it's actually a rigorous mathematical notation. It's very powerful. And the idea is that anytime we have an n-index tensor, we use a shape. And we can pick whatever shape you want. It's not that important. And then all the numbers you can think of as living inside of this blob. You access which number you want to access by each of these wires or lines. And you have as many lines as indices in each line. So a vector is a shape with one line, a matrix is a shape with two, a tensor is a shape with three lines. And the orientation of the lines is not usually all that important. It can be in some more esoteric settings, but usually it's not. You just draw the lines coming out any way you want. The main rule of this notation, besides the lines being indices, is that when you join the lines, it means a sum automatically happens on the joined lines. So it's actually a kind of a relative of Einstein notation. This J should be a subscript. That's a little typo. But the idea is that you see the letter J is repeated here and it's summed over. That's the same expression on the left. So Mij is this green circle and there's two indices. That's V, it's this purple vector, and it's joined on one index, J, and then you can see by inspection that there's one index left over. So you can see just by visual inspection that the result is another vector. There's one index sticking out. So it's like a visual proof that a matrix times a vector is another vector. So that notation helps a lot because then something like this, which would be an n-dimensional hypercube of numbers, which you can never draw, we can just draw this shape with n lines and we're done. So it's a nice way to notate very high order tensors, lots of indices, and to write very complicated sums without having lots and lots of sigmas and having to think of letters for all the different indices, and having indices with subscripts and all of that. Okay, that's the notation. So back to the idea of tensors. An n-index tensor requires exponential memory to store and exponential work to operate on. That's just known in math, it's just by simple counting. So that's the tensor way of saying that you have the idea of the many-body problem, right? The idea that working with quantum systems scales exponentially in a naive way. So that's all. So the idea is that when we see this big tensor at the heart of a wave function, naively, we have a many-body problem. We have what math people call the curse of dimensionality. You have a tensor with too many indices. So we want to try to break that curse of dimensionality. We want to break the many-body problem. So there's a hint that we have just from mathematics, which is we could take a tensor with two indices. That's a matrix. And we could say, how do people compress matrices? They do things called matrix factorization, singular value decomposition, QR, rank revealing LU. There's all these different compressive matrix factorization. So I'm not going to spend any time on the math of that, but hopefully you've maybe heard of those a little bit. And the idea is that you can take a matrix, you can analyze it, and you can find that in many cases you can write it as a product of two matrices that share a small index between them. And by doing that, you can prune away columns and rows that you don't need, and you can use fewer parameters and store this matrix as a product of two smaller matrices and save memory and save in computing time. The thing that people are waking up to now in the last 10 years in both math and physics more and more is you can use this trick very widely on tons of objects, not just quantum wave functions. It's been a surprise to me to learn from the math community just how many things you can use this on, actually. The idea is that you can recursively do the same thinking on a tensor. So you can say, let me view this as a large matrix where this is a row, and then all these indices together are one big column together, and just conceptually. So I can do a matrix factorization there, but then I have another tensor left over. I can do the same thing on that, and on that, and on that, and on that. And without going into too many details, I can just do this chained recursive matrix factorization. And in the end, you do some counting and you realize you actually have exponentially fewer parameters that you now store. You have just polynomial parameters you store in these small tensors. But if you could multiply them all back together, you would be describing some big tensor. So you're describing a special family of these big tensors. So in terms of wave functions, you're finding a special class, a special manifold of wave functions that could, you hope, is very powerful. Maybe it's the class nature actually uses, or not. But it turns out that it seems to be actually a very good class to use for many problems. All quantum circuits of low depth, all ground states of gapped and local Hamiltonians in one dimension. Many things like that. All equilibrium states of thermal systems at long times, in one dimension. So many things actually turn out this compression is the right compression for many physical processes.
Can I ask about that? Do you mean in the basis where the indices correspond to individual particles or individual spins?
That's right.
Preferred basis in which that statement is true, because clearly it can't be true in all bases.
That's right. So it kind of, you're right, exactly. You're right, it's not true. It's true mostly in the basis where the Hamiltonian is local and short range. Exactly. So it's an interesting story. I mean, so yeah, like Steve White had described it to me one time in a way that helped me understand it really well. He said that there were methods in the 80s and 90s that were trying to do renormalization group based on Wilson's NRG and other ideas. And the idea was, let's just look for entries in the wave function that are small and throw them out. And what he said is that that was almost right, but you had to do a change of basis first. And then in the new basis, now a lot of numbers become small and you can throw them out. But in the old basis, it may be that all the amplitudes are about the same size. It's just that many of them are the same amplitude over and over and over, looking like they're different, but actually it's low rank, so they're really the same. That kind of idea. So on the one hand, these indices, the ones sticking out, are in the original basis, and that's very important. They have to be. If you mixed up the basis, this compression would fail. But on the other hand, these internal indices, we call them virtual indices or other names. These are discovering another basis inside. There's like an inside basis, like a latent basis. And that basis, the wave function is compressible. So sort of uncompressible in the original basis, highly compressible in the new basis, all at once. So thank you. Great. Yeah.
Is it special for one-dimensional systems?
It's mostly working in 1D and on trees. So any lattice that has no loops, that's going to be important later in the talk, actually. So we can do trees in most any dimension as well. So the reason 1D works is mostly because you don't have loops. When you go to 2D, things have loops, square lattice, triangular lattice, and it also works there, but we are pushing the technology a lot. So I'd say it actually works very, very well there too. It's just that the methods get more expensive. So there's an interesting kind of balancing act right now about we can either do the expensive methods in 2D based on these, and often they work, but we have to be very clever about which problems we choose to go after. Some go great and some just fail really miserably. But now we're finding we might be hitting a new time where we're actually finding cheaper methods to do these in 2D and 3D. So it's kind of an interesting time, actually. But historically, they've been mostly very low dimensional. Okay, great. So now the connection to quantum computing particularly, let me kind of start to make that argument for a minute. So how do we actually optimize these? There's actually tons and tons and tons of algorithms to optimize these. But let me just show you like a very simple one in kind of one slide. So one way to optimize these, meaning get the numbers to be what we want, is to just apply gates. So we can always take like a quantum evolution, whether in imaginary time or real time, and we could do like a Trotter decomposition on it, break it up in time steps and break it up into like Hamiltonian terms. And we can make gates. It's just like how you would do quantum simulation. And then we can apply these gates in imaginary time and we can push to the ground state, or we can apply these gates in real time and we can evolve the system in time. And so I just wanted to say that in one slide. I don't have time to really show all the theory, but the main point to understand about how we do that is, for us, a gate, so we might act gates on all the different bonds, all the different sites, as you evolve. So at some point in the evolution, we might be acting a gate on 2 of the sites, say these 2, and we can do that very efficiently. All we do is we remove 2 of the tensors from this tensor network out, and those, because that's the only ones that the gate touches. And then this is just a contraction of 3 tensors. The gate is a tensor, we can map it to a tensor. There are these 2 tensors making up the network. We just do this contraction, it's just some matrix multiplies and some things like that. Afterward, we get a big tensor with 4 indices, we decompose it back into these 2 again. They will still share an index, but that index might grow or shrink, but usually it grows a little bit, and we can kind of prune it back. And then we just put those back into the network. So that's the kind of, just to give you a flavor of like what the algorithms look like to code, we just code this contraction, and then we do some matrix factorizations, we get new tensors, we put them back. Then we just can apply a gate on the next bond, do the same thing, put it back. Yes.
That says approximately equal. Is that what you mean?
Mm-hmm.
Okay.
It is, because when I say approximately equal, I'm imagining here that we break this thing back into these 2 new tensors that are colored in a different color. And when we do, we can do some analysis and find that we also want to truncate. We can adaptively size the new index that goes between them. And we can choose to keep that to be an equal sign, but then our costs will grow very fast. Or we can make it approximately equals with a very small error that we get to control. And we make an error, but it keeps our code running really fast. So we were able to like choose between error and speed in a really nice way. Yes, thank you for the questions.
And when you say that it broadens in the middle, you mean just there are more indices now?
Oh, sorry, I just meant the index has a higher dimension. So it just becomes like, if you think of these as sort of roughly as matrices, they become like just bigger matrices. Yes.
when you introduce gates, do you have to like keep track of the norm all the way?
So that's a good question. You usually do. So usually we just fix the norm back to 1 after the gate. So we make some error, but we just correct that. We can easily correct that by just computing an overlap. So that's an important thing to know about. And then interesting though, in other cases though, we can let the norm just drift. And you can actually do math problems where you can compute integrals, or you can do counting problems and things by actually measuring the norm at the end and seeing what it was. So you can do math problems that way, by letting the norm not be 1. Okay, this is a good point to ask questions on that. I didn't want the whole talk to be too technical, so I just was going to give you like a very cartoon flavor of how we do some of the optimizations. Okay, great. And I'll talk a little bit about other ways we do it later, but that's going to be the main way we'll use when we mention this quantum utility method that I talked about earlier. So one point I wanted to really think about for a minute was we've been realizing more and more, kind of waking up to the fact that unlike some other classical methods, say perturbation theory or something like that, tensor networks seem to be kind of eerily similar to quantum computer, like in certain ways, and I'll tell you some of these ways. So one way is, let's say, what's one thing you want to do in a real quantum computer? Well, you'd want to prepare a simple initial state, maybe a product state. Sure, you can do that. You can apply gates, yes. So any kind of gate, we can even do long-range gates. So any gate from the quantum computing toolbox, time evolution gate, control Z, Toffoli, any gate you want, we can apply in kind of order 1 time efficiently, and even adapt our resources afterwards. So we can use kind of the minimal resources to keep always below a certain error threshold. That goes well. So no problem there. What about sampling from the wave function? So these are the main things you would do, right, in a quantum computer. So afterward, you want to take a sample. You can definitely sample from a tensor network. Even better, it's actually perfect sampling. So those of you who know about sampling, there's no Markov chain for a tensor network to sample in this case. You just draw 1 sample, and it's already a true sample from the distribution that the tensor network captures. So that's very powerful. So just like a quantum computer, you're really drawing from the actual distribution in 1 shot. So that also happens. Even things like, if you allow small errors to happen, it makes things easier. That's certainly true for a quantum computer, right? If you get your errors down to a certain point, but then stop, that's easier than trying to continue to get them to 0. Same thing with a tensor network. If we accept a certain little bit of error at each step, that keeps our indices small. So that also holds between them. Then there's ones that don't hold between them. And here I put ... because there's quite a few that are only the tensor network can do. We can apply non-unitary gates. We can actually post-select efficiently. We can solve counting problems, many other tricks. We can machine learn wave functions into a tensor network in a way that doesn't involve any gradient descent and uses an active learning method. I mean, there's all kinds of things extra that we can do that are pretty interesting. And then last but very much not least, what's on the other side? What can a quantum computer do that a tensor network can't do? And that's the big one, handle high entanglement. That's the thing that we can't do, basically. So if you have to run some process that maybe involves applying gates and things, and it runs you off into a regime where the entanglement is very high, that turns out there's a whole theory that explains that when we try to represent wave functions by tensor networks, what makes the amount of parameters we store big and small? And it's entanglement. So if the entanglement is big, we have to use a lot of parameters, or we have to make huge errors, like drastic errors. But that's what a quantum computer in principle should be able to do. And I put both yes and no here because it should be able to do that. But as far as I know, correct me if I'm wrong, but as far as I know, even these results from Google, they did prepare a state with very high entanglement, but they really prepared something like a fraction of a % of the state with high entanglement. So it still has a lot of entanglement, but it's not like the circuit ran with very low error. I mean, they actually enormous errors in terms of the fidelity to the target state. So what I'm saying is that you can certainly make a quantum computer reach high entanglement, but high enough to, how high is sort of still a little bit of a frontier of exploration. So I'm just saying, I think that's still something that is being mapped out. But we're a strong, no. Like, if you go to extensive entanglement, you can't represent that. Not for a specific pure state, that's for sure. So maybe you could put a little asterisk on this here because we have other ways around high entanglement. That's a whole talk as well, where sometimes you don't actually want to store a highly entangled state. You might just want to store a subset of its properties. Like maybe it thermalizes and all its properties are determined by a temperature. And so we could throw out memory of the initial state that thermalized and just remember the temperature. And then we could actually sort of store a high entangled state that's a whole story, but it's a little more subtle. So, but the point is that when I look at these capabilities, I have to ask, if we put a quantum computer in a box, I'm not going to tell you which box, and a tensor network's in the other box, could we tell what's in each box? You can, it's just for what problems, and that's what I'm saying. I mean, certainly there must be ways to tell, but problem by problem by problem, I think one should ask this question, for each problem that you propose to do. So that's how we should be thinking of, like, since we can do all these things the same, we better focus on problems that have high entanglement. Otherwise, we can simulate it. That's one point. Yes.
Could a tensor network in higher dimensions mimic entanglement of a quantum computer in lower dimensions?
Yes, that's a good question. Right, we certainly can. So that's kind of partly that's some of the more fancy algorithms that we do. So I just mentioned the one about applying gates. But another thing you can do is you can use this kind of d to d plus 1 quantum to classical correspondence, and you can also make a 2D network that's a classical thing that represents a quantum 1D or a 3D. That's something else you can certainly do. And that actually is a real rich, deep area right now. It leads to a whole topic that you could call sort of process tensors or influence functions.
And that doesn't turn the red X green?
It kind of starts to in some cases. So maybe this I should have maybe put red X asterisk, because again, it starts to be a little problem dependent, and mainly if you're willing to not ask for the whole state, but you're willing again to ask for like certain subsets of properties in states, or properties of families of states that are in some kind of equivalence class, by which I mean like states which are like, how to say it, like again, thermalizing states is kind of an equivalence class of pure states, because it's saying all these pure states are different, they're all orthogonal to each other, but if you measure a local property, that local property is determined by the temperature, something like that. So if you ask that question, we can maybe turn that red X back green again. Yeah.
Before you said that tensor networks are good, say, in describing ground state, but ground states for local Hamiltonians, they tend to be highly entangled. So
No, ground states of local Hamiltonians are actually low entangled in general, usually low entangled, actually. So in 1D, there's a proof actually of this. So even, for any kind of short finite range Hamiltonian in 1D, ground states that have a gap, ground states are provably area law entangled, meaning, and that's equivalent to saying that a tensor network can represent them with like a finite internal dimension.
that's what
No
I
problem.
mean, highly entangled, but okay.
They are quite entangled, but I would basically call that like moderately entangled. Moderately in the sense of they're not extensively entangled. Extensively would be just like the same entanglement as a completely random state in the Hilbert space. That's what I would kind of call high entanglement. Whereas the kind that we can capture are quite entangled, but much less, like kind of than sort of a random, completely random state vector or something. Okay, thank you. Great. So that was kind of the point, is not to say we can never tell them apart. It's just saying we should keep asking this question, is what I'm saying. We should go to different problems and say, for this class of problem, could we tell the classical simulator from the problem for that class, for this other class? So let me now briefly tell you about a class where the answer is kind of no here. This is just a few slides on this one result. So this is actually work with Steve White, who was mentioned earlier, and his very talented, at the time, undergraduate student, who's now a grad student at Caltech. We just did this last year. And we weren't kind of setting out to do this, it just kind of fell out from something else we were trying. So we were actually trying to simulate Shor's algorithm, and we kind of knew we weren't going to be able to, but we just thought, let's try, fail, and then see what happens. And then on the way, we actually found out that half of Shor's algorithm is classically easy. That's what we kind of figured out by accident. So that half of Shor's algorithm is a thing many of you may have heard of or know well. It's called the quantum Fourier transform. So what this does is it takes a function that you represent as a bunch of bits, qubits, that's each of these lines, and I don't have time to properly go through it, sorry, but there's a complicated circuit you can look up that mostly involves, say, Hadamard gates on some of these lines, and then controlled phase rotations acting across all the pairs of things. And then after you've done this, if you input a state that represents a function, afterward the state will now be the discrete Fourier transform of that function. So if you input a state where all the amplitudes are flat, afterward it'll be a Fourier transform of the flat function, that kind of thing. Or if you put a delta function on one of the amplitudes is 1 and the rest are 0, afterward it'll be like a plane wave, that type of thing. So it turns out we just took this circuit and we mapped every column of the circuit to a tensor network in there's a straightforward dictionary. Like literally a Hadamard gate is just a matrix with 4 numbers in it. 2-qubit gates are just matrices. This is just a tensor with 4 indices, that kind of thing. And we just took each column and just had the student just represent them as a tensor network and use a code we had to just multiply them together. When we were done, we got a tensor network called the MPO. It just looks like this. It's a chain of tensors with 4 indices each. And the bonds connecting inside all had size 8. So the amount of parameters was extremely small. And what we could do with this is we could take a function, some smooth function, any function you want is smooth, basically, even if it has a few cusps or discontinuities. We could encode it as a tensor network state of n qubits using what's called amplitude encoding, and that's sorry, I don't have time to properly introduce. And when we did that, we could apply that tensor network form of the quantum Fourier transform, and then we could take the same function and do the fast Fourier transform. That's this green curve. And the fast Fourier transform scales roughly linearly with the number of grid points you use to represent the function. But here I'm ramping up the grid points exponentially across the bottom. So because the number of grid points we're pushing up exponentially, the fast Fourier transform cost goes up exponentially. And the fast Fourier transform just has the same cost no matter what function you give it. You just give it any function, it just does what it does. With this quantum Fourier transform, we had coded different functions. Here's 2 examples. One was just a smooth, like a cosine. Another one was the sum of different cosines times these cusp functions, so a really bad function. And we encoded them as wave functions, turned them into tensor networks, acted this quantum Fourier transform network on it, and we get the same result in compressed form in a fraction of the time once the number of grid points is larger. And it turns out the scaling is different as well. So we actually scale an entire factor of n better, where n is the number of grid points. So we actually faster than the fast Fourier transform. So the idea here is that we took a quantum algorithm, pulled it all the way back into the classical world, and when you simulate that, it's actually faster than the previous known fastest classical algorithm. So it's like we're harnessing the power of a quantum computer today on a laptop using like a tensor network operating system. That's kind of the philosophy of that. And then a lot of what's going on in that topic is not due to us. We just contributed that one little part. But even for a few years before, there's been this rapidly developing topic that people call quantum-inspired classical algorithms. And this topic involves this idea of turning functions into tensor networks through amplitude encoding, like represent as a wave function, turn that into a tensor network. And then you can do all sort of quantum-inspired things. Like people are simulating Navier-Stokes equations this way, representing functions like Green's functions of quantum systems. So that one's a bit of a mind bender. So it's like the Green's function of a quantum system is just a regular classical function on a classical computer. You turn back into a wave function, you compress that as a tensor network, and then you store that. And that turns out to be a very good way to represent Green's function. So it's like, it's kind of like quantum on top of quantum. And then maybe one of my favorite ones right now is one of my colleagues, Xavier Weintal, just this August has a paper about using amplitude encoded functions to be orbitals for quantum chemistry. So instead of using Gaussian type orbitals, if you know about this topic, you can use these and they can handle sharp cusps very efficiently. And so he's doing a simulation of a H2 molecule, for different numbers of orbitals. And here's the traditional family of sort of all these different sophisticated Gaussian basis sets. And the convergence to the continuum limit is okay, but it's much slower. And then there's their orbitals just plunging down to like getting to machine precision pretty soon, just a few orbitals. So yes.
Can I ask about the FFTs?
Sure, absolutely.
So I mean, FFTs are one of the most widely used numerical algorithms.
Correct.
There is. Yeah. Is this going to take over?
That's a really good question. I mean, we don't know. I mean, I showed this to our math center, and they were pretty interested, but then only a few of them really followed up. And so I was wondering the same thing. I'm like, are we not seeing something, or what's going to happen? I think sometimes it's what I'm learning is that people in some other communities, they want really, really black box things. So they want to be able to say, I can guarantee you the speed, because this is true, for the FFT, you can guarantee the speed no matter what function the user inputs, even if it's random points on the grid. And you cannot guarantee that with the QFT, the quantum Fourier transform. The function has to be compressible it has to have like a low bond dimension, low rank tensor network form. That's true for a wide class of very wide class of function. There's proofs about that, but it's not true in an absolute sense. So we're sort of, it's one of these things where you try to do something interdisciplinary, and then there's like this sort of culture clash at first about what people want. So I still don't know. It's like we're just trying to find that out. But I think it could have a lot of potential uses.
When it's worse, it can be worse than, is it much worse?
Yes, it can be much worse. If I had a longer, I have a little bit of a longer talk on this where I should have probably just included it, but if you have we also just tried compressing a random function so it doesn't compress at all. And then the scale, the cost for that is way back up here. It like goes exponential and is much slower than the FFT. If you just put like random data and try to Fourier transform that.
Why don't you just run them both and see if you finish first?
Well, let's see. So we're kind of doing that now. We're trying some traditional methods to do differential equation simulations, and then these methods and kind of racing them a little bit. And it's been kind of fun because we're having some of our math colleagues try to propose hard cases. Like they'll say, okay, do the Schrodinger equation with two wells that are very separated from each other, and then you have some function here and some function there. And I'll tell them, okay, that's going to be really easy. And they go, no, it's going to be hard. And we do it, and it takes like a second to do or something. And then, so they're pitching us hard cases right now, trying to break our thing. And so far, it's worked really well. So we're trying that out.
Can I ask a quick question here? Since you brought up the fast Fourier transforms, could this be useful, like in doing classical molecular dynamics simulations, where you're using Ewald summations to calculate the electrostatic interactions in the system? It's a classical simulation, but for the electrostatics, you're using basically Ewald summation and then this kind of discretized particle mesh Ewald to do the calculation of the electrostatics. So basically, could this the QFT's approach be useful in actually be implemented in classical molecular dynamics simulations?
So I think I have a sort of a disappointing but interesting answer to that, actually. So I was thinking about this last week. So I saw a really good talk by Leslie Greengard on Ewald summations, because he's sort of the master of that, because he invented a thing called the fast multipole method. He's the head of the CCM Center at Flatiron. After seeing his talk, I think that if you use this technique to do Ewald summation, it's the same as the fast multipole method. Like I think when I say the same, I think it's the same algorithm. So I think more or less, I could be wrong about that. I mean, this is just me thinking for a week, so I could be totally wrong. But I think this actually has the connection to that's one of the best known methods to do Ewald summations of point sources. So I think that this is another way of discovering the fast multipole method. However, I think it can also possibly bring some new directions to that method, like using it in other cases that maybe people weren't using it before. Does that answer your question?
Yeah, it does, but I have to now think about it even more. So, but thank you for bringing.
Yeah. So when you write a tensor network in a traditional form, I think I mean, this is me learning this stuff pretty recently. I think it's what they call like kernel like multi-scale kernel splitting or something like that in the Ewald solution. But I think when they say that, they might be describing a tensor network and just not using that language. So I'm kind of trying to explore that connection right now, actually.
Okay, great, thank you.
Yeah, it's something I want to figure out. So if you want to follow up, we can talk about it.
Yeah, I think I will email you. Thank you.
Great, absolutely. I mean, there's not a total free lunch here. People that are doing the fluid simulations are finding that once the system becomes too turbulent, that the tensor networks also hit a wall, kind of have to, almost by some information theoretic reason. But it's very interesting in these cases, like this paper that's in Nature Comp Sci from last year, I should watch my time. They find that the size of the tensor network parameters you need actually scales with the Reynolds number. So it seems to really know something about the physics. It's very interesting.
Wow.
So let me now go to this main last part and try to be fast about that. So this was now by request. We've been trying this out on other problems, this technology of tensor networks and quantum simulation. And one thing that happened recently this summer was we tried it to simulate Ising dynamics on heavy hexagon lattice to help answer this question of, have quantum computers demonstrated utility? So this was work with Dries, who's here in the room, and then a really talented postdoc, Joey Tyndall at Flatiron, and with Matt Fishman, who's the head of he's the lead developer of the iTensor software and software staff at Flatiron CCQ as well. And this method is described in these two papers, this short preprint and then this longer methods paper. So there was this kind of sudden, coverage of this paper that just kind of appeared in Nature in June. And the paper was very carefully worded, I have to say, and much more careful about what was claimed. So I would say go read the paper because it's very careful, and the conclusion of the paper is very good about making these points. But then, as can happen in fields that are very hot, the coverage by the media and various media was a bit more strong. You know, like they would say things like, on the cover of Nature, it said, probe the physics classical methods can't reach. So classical methods can't reach. Another article said, beat a supercomputer. You know, so that of course attracted a lot of attention because it's like, now this particular quantum simulation beat a supercomputer. Classical methods can't reach. So, you know, that got our attention too. And I had just been encouraging Joey to work on a certain method for a different reason. And then Dries, you know, alerted us to this paper. So Joey already had the method and he tried it out. And so it turned out we were able to sort of answer back. What did the experiment compute? Briefly, it's just taking like an Ising model and decorating it on this lattice, which is the lattice of connectivity of this certain processor called the Eagle processor up in, that IBM has developed. And you do what's called flow K dynamics. You basically do a sort of alternating time evolution of the kind of ZZ traditional classical Ising part of the dynamics, and then a sort of a stroboscopic quantum part of the Ising dynamics where you apply a field in the x direction in between. So you switch these off and on. It's not continuous quantum time. It's sort of like a stroboscopic quantum time. And the qubits in the experiment play the role of these quantum Ising spins, and they have these non-commuting operators, and the entanglement generically could grow in time. It turns out not to, but it could. And so that's the sort of briefly the setup. They did something also very nice in this paper that's you know, it's been done a little bit before, but this paper was one of the best demonstrations and uses of it that I know of, which is this idea called zero noise extrapolation. So instead of having the noise and the errors in your quantum computer be purely a negative thing, you actually use it as another piece of information. You say, let's take that weakness and turn it into a strength. So you say, what we can do is we could even, I'm not an expert in this part, so you know, just from my theorist understanding is you have some amount of noise, and instead of trying to always get the noise to go down, you can also turn it up. You can say, let's make it worse, and let's do a number of experiments at less noise, more noise, and then extrapolate back to zero noise, which is a very smart idea, and it works quite well in this work. So they're able to consistently get much, much better estimates by just doing experiments at different noise levels and extrapolating backwards. So then they run this flow K Ising dynamics, and they run it to some short times and using some simple ideas about working within patches of the system that are the only ones touched by the light cone of the dynamics. You can get totally exact results at these short times, meaning short numbers of circuit applications. That's this black curve is the exact results. And then the quantum processor with the noise mitigation is blue points, and it sits right on top, almost right on top. Those great, really great results from the quantum computer. No argument about that. And then they also benchmarked against two particular pretty state-of-the-art tensor network methods, matrix product states and a certain kind of 2D tensor network called ISO-TNS. Those can work really well in some regimes, fail a little bit here, and then in other regimes and for other quantities just really fail almost completely. So in certain quantities like these 3 poly operators that you measure on 3 different sites of the system, or sorry, more than 3, like all these subscripts are many poly operators, sorry. All X is on all these sites, Y on that site, Z is on these sites. Then the tensor network, these particular tensor network methods failed like almost completely. So then that was some of the evidence that they're starting to reach quantum utility, meaning practical problems that the classical methods are struggling for. Then they went to much longer times, something like 20 layers of this circuit, and could keep getting good results with the zero noise extrapolation, while the tensor network methods, you know, could do sort of okay in some regimes, quite poorly in others, and then drastically badly for more complicated observables and at certain parameter regimes. So, you know, they could really find regimes where the tensor network methods really struggle. And that's all correct and true. So we, you know, Joey got interested in this with some other, he said there's other methods besides those 2 tensor network methods. We also could have tried these 1D tensor network methods like the ones I mentioned earlier, where you just chain a 1D chain through the 2D system. However, the cost of those grows exponentially when you do a large 2D system. The IBM system is quite large, very large. There are these 2D tensor network methods. Someone asked about that a minute ago, called PEPs or tensor network states. They have different names. But the algorithms for those are quite expensive. So that's really why I would guess or say this 2D tensor network method, that's this fuchsia line, this red curve, you can see it's kind of working. I mean, it's tracking the upward trend. It's not because the method is bad or really failed, it's because it's expensive. And so you can't push the parameter count quite as high as you would like without burning up a ton of computer time. And the scaling isn't very good. So you get a certain point, but it really starts to, the computer struggles and you have trouble pushing it. So these 2D methods, a lot of them are expensive when you do them in a highly controlled way with a lot of accuracy. So our basic idea was, let's just do it in a less controlled way. And we can do it much, much cheaper. But we're not quite as controlled as before. So we were able to do the same system to very high accuracy in practice. How do we do it? First of all, we started with exact same topology as the experiment. So instead of snaking a 1D network through a 2D, we actually just made a 2D tensor network that's exactly the same topology and geometry and everything as their experiment. That's sort of one key thing. So did the ISO-TNS, as far as I understand it. We did that as well. Then to compute properties, first of all, let me just sort of say, the main thing you need to do is you need to be able to compute the overlap of the wave function itself. Once you have that property, a lot of the other things we need to compute, say to optimize the numbers, follows from being able to compute this. You just compute this with one removed, or you do other little variations like that. So let me draw that in a top-down view. Ideally, we'd be able to just contract now most of these tensors we judge, or do all these sums. When you're done, we'd have this environment tensor, this black object is one tensor with 4 indices sticking in, and then one pair of tensors, or a tensor inside that we want to operate on to optimize its parameters. That would be the one left over in the middle. That'd be the thing we wish we could do. And sort of you do that in that more expensive method, that ISO-TNS. You do something quite close to being able to do that in a very controlled way. We said, let's do something very drastic. Let's just take that, what's called environment, which is everything else outside contracted down. Let's completely factorize it into just 4 vectors. And in the parlance of this thing called belief propagation, which is an old method, it has other names, cavity method, these old names from spin glass literature, they call these messages, these little vectors. So these are like a very poor sort of cheap approximation to this true environment of the rest of the network. Okay. But then the neat thing about belief propagation is that you do this cheap thing, but you do it self-consistently. So it's kind of like mean field theory, but in a tensor network language. So you have all these tensors now surrounded by these messages, but let's say we don't know the messages, so we put random numbers into the messages, we don't know them at this point. Then what you do is you say, well, if they're self-consistent, the contraction of these 3 messages around this tensor, that's a vector, because see there's one line sticking out. And that could be this vector, so we can replace that vector we can send the message over. We do that everywhere in parallel. Then we make messages going down and we send them down. We make messages going up and we send them out. So we just run that process around and around and around and just measure whether the numbers are changing, and after a while the numbers stop changing. And we say maybe these messages are converged. So it's like a cheap mean field approximation to that environment tensor. Then once the messages are converged, we can sort of open up a little bit of the true network back together, and we can apply a gate to take one step in time. We do this gate on all the bonds that have a gate in the original Ising dynamics that IBM set up. We apply all these gates, we take a step in time, and we just iterate that. That's basically how the method goes. Of course, I'm skipping over many technicalities, but that's the spirit of it. Okay. Slides are not advancing anymore. Oh, I think somehow Zoom pulled me into I'm painting on my slides. The other little red dot somehow is drawing on my slide. I don't know. Okay, so that red dot's going to be there the rest of the talk. Okay, so basically, I'll try to finish up real quick. So belief propagation method, it's fully controlled if the lattice had no loops, but it does. You can still run it on any lattice, and then it's just sort of a semi-controlled method. It's very cheap. We can push our representation quality of the wave function very high. But then what we're doing is we're storing a very accurate wave function. It's just when you actually go to look at its properties, that we do in a kind of an approximate way. So sort of an interesting balance. It's like mean field theory, but probably much more accurate than traditional mean field theory. And then we can do dynamics on top by applying these gates sort of in between the mean field steps. This is not totally our method. It's really thought of by some other folks. And we were just interested in having a kind of state-of-the-art implementation. We tested it. This was a suggestion actually by one of the people from the IBM paper. We tested it on some really small loop systems, and it actually, the exact results deviate after a certain time from it. So you can see it's not controlled. It works really well at short times. Then at longer times, our method goes down, the exact method goes up, it deviates. So that's what I meant about it's not exact on a loopy lattice, it's only exact on trees. But then something very strange happens when you do 2 loops. It matches to the exact results much more. And then on 3 loops, it really tracks the exact results much, much better, even to late times. So we don't know why exactly, but maybe there's some kind of interference phenomenon happening where even though it fails on one loop, when you have lots of loops, somehow the tree approximation where this method would be exact kind of comes back. So there's some kind of dynamic something subtle that we don't fully understand. So it's a little bit of a lucky thing that happened here. This just goes to show how close the race is between quantum computing and classical. We got a bit lucky that this sort of semi-controlled, not fully controlled method just happens to work on this lattice quite well. Okay, yes, I think it's being recorded to the person asking this. Okay, great. And then I'm not sure how to. Okay, good. Okay, so almost done. So basically, we can do the verifiable regime, and it only takes a few minutes in that regime running on like a laptop. And we just get results right through the exact results, just and very close to the quantum experiment. And then the interesting part is we can also go to these larger depths, and we keep getting very good results. And now, after doing some extrapolations in our parameter account, we think that we're in the top 1 or 2 most accurate methods that have now been published for this. And we're agreeing with the experiment where it seems to be right, and then we're even having some places where we think we're more accurate in the experiment, actually, just based on some other methods that we cross-checked with and things. These are harder calculations. They require running more like order of a day or 2 days on a Flatiron cluster node, but not like the whole cluster, just one node or something. And there's some extra tricks I won't explain, but they're in the paper where we actually do some extra time evolution to map multi-site operators back in time to a single site operator. So we didn't actually have to measure multi-point operators. We just measure a single site operator under some extra dynamics that maps it to multi-site. So we do some tricks like that as well. And then after our paper came out, which Joey was like really fast to getting it out, it was like 2 weeks. I was really shocked. I mean, I helped him write it, but he just had the results like that. Then a bunch of papers came out over the summer, getting many of this very close to our results, and in some cases very, very closely. But using an interesting stable of other methods, some other tensor networks, but also Clifford perturbation theory, which is where you do perturbation theory around the Clifford point, where all the gates just rotate Pauli matrices into other Pauli matrices. So there's lots of interesting attacks in a sense on this dynamics. So in summary, we found that apparently this dynamics on this lattice is very tree-like. It's as if the loops are there. Of course they're there, but they don't seem to drastically change the dynamics from if they weren't there. We have this very fast and cheap tensor network method that seems to be very effective for the dynamics in this case. So now we're interested in trying it on other 2D systems and studying their dynamics. So I'll just leave out these well, I should say these thoughts and then I'll finish. So basically, tensor networks are helping to define this boundary between hard and easy. I think it's really important to help the field of quantum computing because we'll help them steer toward targets of the best opportunity and best use of their resources. And then purely on the classical side, we're interested how many quantum algorithms like the quantum Fourier transform might be brought back into the classical world. And maybe we can get some benefits of quantum algorithm research now, like today, that way. So thank you for the questions.
Yeah, questions.
Yeah, so before you said like the main problem is getting the big entanglement there, right? So what do you think is happening in this very hexagonal lattice? Like why are you so good? Like is there some kind of structure to the entanglement that you basically like explore, which is like very fast for tensor network, but that's why I think exactly.
Yeah, it's a really good question. So the question is, is there something about the entanglement of this dynamics in this heavy hexagon lattice that we're exploiting? As far as I know, I mean, this is, as far as I know, the entanglement is, moderately high. I mean, it's somewhat high here in a normal sense for short times. So I think partly we're just able to do something kind of a subtle thing at 2 levels. I think we're able to capture all that entanglement quite well by having the bond dimension or the size of these indices inside of our tensor network to actually be very big. It's like pushing up into the hundreds, which is unheard of for these 2D methods, for the more controlled 2D methods. But then what we do after we make this really accurate representation of the wave function, we do a much less reliable summary of its properties. So we sort of like do this belief propagation thing where we pass these vectors around, which is a cheap, rough approximation of the rest of the system. So we make this really accurate state, but then we kind of extract its properties only approximately in a sense. And I think those help each other. Like I think by doing this approximate peak at this really accurate thing, those 2 things help each other out. But then there's a third thing that's going on that later this came out when Joey studied the system a bit more. It seems to be that although the entanglement grows in the dynamics at first, it actually plateaus. So it may be that for this system, because this has been seen in other systems, there's 1D systems where entanglement can plateau. It doesn't generically plateau, but it can. And there are these things called like pre-thermalization dynamics and things like that, where entanglement can actually plateau for a very long time. And then finally, at very late times, it has to grow exponentially, but or linearly off to a very large value. But it can sort of get trapped or sort of stuck for a while and be flat. So maybe that's happening in this particular system.
So it's like pretty much dependent on the topology of the lattice.
It's dependent on just the particular Hamiltonian on that lattice. So,
Yeah.
some Hamiltonians on some lattices and some dynamics just do this.
For the high energy people, actually the reason it happens is because of confinement. They're actually quenching into a phase that's confined.
It's
And
like
so
the excitations
excitations
self-trap.
can't spread because they're confined. And
Right.
so that's actually a paper we're currently working on to show that this could never show large entanglement growth because you're quenching into a confined phase, like quasi-particles.
But is it just the connectivity or is it just?
No, it's just a
Hamiltonian?
property, it depends on any
Nearest neighbor.
connectivity. So that's why it explains why we don't see the effect of loops. Because there are loops, so they should be wrong, but the loops are irrelevant because there are no quasi-particles that can run around the loop.
The quasi-particles don't make it all the way around. So,
So when you show the plot for FFT versus QFT, what is the memory complexity of when you compare with the tensor network with the FFT? Like, would that be a reason to kind of think about where you're spending more?
you're actually also saving on memory by quite a lot. So I think roughly the number of grid points, if you call that n, the amount of memory here is log n memory times some prefactor that has to do with the complexity of the function. And then the cost of the QFT is also log n. Because that's the interesting part, is the FFT is n log n. Right? This one's just log n. This has a worse prefactor by a lot, though. But that's why they don't, why it starts out above, but later it goes below, because the scaling is much better.
And that's one question.
Okay. And there's a question if you can catch that, or I'll look at it on the same.
So if I have a full graph versus, I guess, these tubes, will I still have the same thing on the full graph or not?
Like, you mean if you have a full graph, you mean like a just fully connected complete graph? That's a really interesting question. So it turns out that Joey, of all people, the same postdoc who did this, he's been doing some other work on, not maybe, I have to check if he's doing complete graphs, but he's been doing very kind of rather random graphs, like these things called Erdos-Renyi graphs, these sort of very arbitrary high dimensional graphs, and finding that actually regular old DMRG, like the usual method we use from Steve White to optimize these tensor networks, works surprisingly well to get ground states, at least on those graphs, which seems very contradictory because the usual wisdom, and I even said it to someone who asked the question, is it works in 1D, it's harder in 2D. So you'd think, okay, it's only going to be harder in 3D and even harder as you go up. But it may be that 2D is the worst. And then it may be that, like mean field theory and a lot of things, when you go to infinite D, it actually gets easier again. So it's like that's there's a sort of attacks from all sides on quantum mechanics, from high dimension down, from low dimension up. There's all sorts of ways to attack the big-body problem. Yeah. I see some questions on the Zoom. Maybe I should.
There's also one more question in the back.
Yes, question in the back.
I'm curious how short algorithm runtime ends up being when you plug in these QFTs. So, as I understand your simulation, is like efficient if the input state is like has only one dimension. But I would guess this isn't generally true. This isn't generally true.
That's right. Yeah, exactly. Because that was the number one question we got when we put this paper out, when we talked about the QFT. Because our title of our paper was something like the quantum Fourier transform has small entanglement, which is true. And the student actually proved it. I mean, he was really good at that paper. He actually made a rigorous proof of it and everything. The main question we got was, does this mean Shor's algorithm is simulable? And to your question, no, because Shor's algorithm has two stages. And the first stage, you do this thing called like modular exponentiation, and you're basically, the way I explained it to the students in the hour earlier is, in my understanding, it's roughly like running a random number generator, like one of these pseudo-random number generators on the computer. And it's just depositing the states, the outputs of the random number generator into your quantum state. And that's not something a tensor network would be able to compress well at all. So you actually end up with a really bad tensor network compression of that. So then you never even get to the QFT part. So if you try to do a simulation, it just bogs down in the first part. That's the answer of that. But then, of course, the neat thing is that you can use the QFT to do a lot of other things besides shores. But it seems like shores, as far as we know, is still off limits for the simulation. Great.
Maybe you want to,
Let me see with the chat.
quick.
Okay, is the QFT exact or approximate? Good question. So let's see. Yes. Okay, I agree. Yeah, it is approximate. We can, however, take the representation in terms of the grid to sort of basically exponential precision with linear cost. So that part we can make as small as we want. Then we can also basically, as far as we know, we can also get the error of the tensor network compression down exponentially in population as well. So it is approximate, but I think we can get those errors down to around machine precision. And then with FFT, you're also working with machine precision things. So now there may be, it's true, I think, that the comparison may not be strictly fair. Like maybe the FFT still always makes even tinier errors. But I think for practical purposes, we can get the errors down arbitrarily small with sort of polynomial effort, things like that. So I think it's in good shape on that. Yeah, it's a good question though.
On that note, maybe let's thank Miles again and